Section: Introduction. In this section, we discuss recent findings that highlight the effectiveness of large language models, LLMs, in handling tabular tasks, such as answering questions about tables. We note that using structured prompts and in-context learning can enhance how LLMs interpret tabular data. Additionally, we emphasize that guiding LLMs through a step-by-step reasoning process improves their understanding of data queries. We also explore the benefits of using external tools to better analyze tabular information. Traditionally, adapting language models for tabular data required changes to their architecture, including special features to understand the structure of tables. However, with the emergence of models like GPT-4, GPT 3.5, and PaLM 2, a new strategy has developed that focuses on creating precise prompts that incorporate table data and utilizes programming languages like SQL and Python. This approach supports more advanced reasoning processes across various LLM platforms, including open-source options like Llama. These advancements have led to improved fine-tuning of models for specific tabular tasks, as seen in projects like StructLM, which enhance abilities in recognizing table structures and verifying facts. However, we recognize that current benchmarks may not fully address the complex reasoning challenges faced by professionals working with tabular data in real-world situations. Thus, we see a significant need to create a benchmark that connects academic research with practical applications. To assess LLM's capabilities in table question answering, Table QA, we introduce TableBench, a detailed benchmark that includes 18 subcategories within 4 main areas of table QA skills. We analyze real-world challenges related to table applications and define task complexity based on the number of reasoning steps needed. From this analysis, we develop a thorough annotation process that combines manual and automated techniques to build TableBench. We also create a large instruction corpus called TableInstruct, which covers 3 reasoning methods. The textual chain of thought, TCOT, method uses a series of logical steps to reach an answer. The symbolic chain of thought, SCOT, method employs programming commands to refine results through a think-then-code approach. Lastly, the program of thought, POT, method generates executable code, using programming lines as reasoning steps to arrive at a final result. Using open-source models and TableInstruct, we propose TABLELLM as a strong baseline for exploring LLM's reasoning abilities with tabular data, achieving performance similar to GPT 3.5. We evaluate over 30 LLMs on TableBench, revealing that both open-source and proprietary models need significant improvements to meet real-world needs. Even the most advanced model, GPT-4, only scores modestly compared to human performance. In summary, we present TableBench, a human-annotated benchmark with 886 samples across 18 fields, aimed at facilitating tasks like fact-checking and numerical reasoning. We introduce TableInstruct, a large instruction corpus covering 3 reasoning methods, and TABLELLM, which serves as a robust baseline for TableBench. We systematically assess the capabilities of over 30 models on our benchmark and create a leaderboard for evaluation across 4 main tasks. Our extensive experiments indicate that a comprehensive table QA evaluation can effectively measure the gap between leading language models and human abilities in real-world scenarios. To construct TableBench, we analyze real-world applications of tabular data, categorizing problems into 4 main categories and 18 specific subcategories. We define task complexity based on the reasoning steps needed for problem solving and provide clear guidelines for these steps, which are strictly followed during annotation. We also introduce an annotation framework that combines manual and automated methods to improve efficiency. Ultimately, we collect raw tabular data from various existing datasets, focusing on tables with significant numerical values to ensure complexity, resulting in a total of 3,681 tables across 20 major topics, including finance, sports, and science. Section Summary. In this section, we introduce TableBench, a comprehensive benchmark designed to evaluate large language models, LLMs, on tabular tasks, categorizing real-world challenges into 18 subcategories and defining task complexity based on reasoning steps. We also present TableInstruct, a large instruction corpus for LLMs, and outline our methodology for collecting and annotating tabular data to enhance the model's reasoning capabilities in practical applications. Section: Question Annotation. In this section, we manually create a more intricate set of questions to reduce the risk of data leaks in large language models, LLMs, instead of altering existing datasets. We introduce a self-inspiration question generation method to develop questions across various categories. First, we carefully design one seed question and a detailed definition for each category, forming our initial question seed collection. Next, we use these seed questions as examples in a well-structured prompt to guide GPT-4 agents in generating questions that fit specific category requirements. We limit the initial output to 5 questions. These questions are then manually reviewed to identify new patterns and added to the seed collection. We consistently select representative questions to maintain a benchmark quality, ultimately keeping 50 questions as our test set for TableBench. Once we reach 50 questions per category, we manually annotate a sample of 30%, while the rest are verified by another GPT-4 agent, which will serve as the questions for TableInstruct. For answer annotation, we create a self-consistency mechanism based on a given table and question. During the answer generation phase, we utilize 3 LLM agents, each using a different reasoning approach, TCOT, SCOT, and POT, to produce responses. We implement a voting system to evaluate the answers from the different agents. If the voting indicates consistency among all agents, we tentatively accept those results. These preliminary answers are then manually reviewed and adjusted to finalize the answer and its reasoning. To reduce bias in the answers generated by LLMs, we enforce a strict format, ensuring only essential and accurate content is included, avoiding any model-specific styles. For answers excluded due to inconsistencies, especially those from overly complex questions, we randomly select 30% of the filtered responses for manual annotation and add them to the dataset. Importantly, we manually annotate all answers in TableBench without omissions and scrutinize each one carefully. Regarding human annotation, we compensated all annotators with 6 per question and provided a comfortable working environment, free meals, and souvenirs. We also supplied the necessary computer equipment and GPT-4 interface for labeling. In total, we labeled about 2,000 questions to assess the quality of the questions and answers, with an overall cost of around $12,000. The annotators reviewed tasks such as multilingual code explanation and code completion. For quality control, we sought feedback from annotators on task instructions and the website's user experience, making iterative adjustments to the annotation guidelines and website design based on their input. We also employed a double-blind annotation process, assigning 2 independent annotators to each generated question or answer, ensuring they worked without prior discussion. We then checked for consistency in annotations, and in cases of discrepancies, experts reviewed the differing annotations to refine our standards and ensure a thorough understanding of the constraints for specific question categories and the validity of computational results. In our quality assessment, we invited 5 internal annotators to evaluate TableBench across 4 dimensions. Given the subjective nature of complexity and objectivity, annotators scored based on their judgment using a scale from 1 to 5, with reference examples and criteria provided. We also reported an agreement percentage and Randolph's kappa with a 95% confidence interval. Our quantitative and qualitative analyses of the benchmark not only demonstrated its complexity but also highlighted the consistency of data annotations. As shown in our figures, TableBench mainly consists of numerical tables, with the largest portions being financial reports and data from competitive events. We developed 4 main question categories based on real-world scenarios and user needs for tabular data: fact-checking, numerical reasoning, data analysis, and visualization, which include 18 subcategories that illustrate the various challenges in table QA scenarios. Compared to existing datasets, TableBench covers a wider range of question categories, particularly focusing on data analysis and chart generation capabilities that are often lacking in previous datasets. We define the complexity of the dataset by counting the number of reasoning steps needed to solve the problems. Our findings indicate that the overall complexity of TableBench is significantly greater than that of existing datasets, especially in questions related to data analysis and visualization. We define table question answering, table QA, as follows. Given a semi-structured table with a certain number of rows and columns, our goal is to generate an answer to a question using the information in that table, where the answer consists of a set of values or entities. Section Summary. In this section, we detail our approach to creating a robust question and answer dataset, TableBench, by manually generating diverse questions and employing a self-consistency mechanism for answer validation using multiple LLM agents. We emphasize quality control through iterative feedback, double-blind annotation, and comprehensive assessments, ensuring a high standard of complexity and accuracy in our dataset, which focuses on various real-world question categories related to tabular data. Section: Reasoning Methods. In this section, we discuss reasoning methods for optimizing input for large language models, LLMs, to produce useful outputs based on specific tasks and examples. We present different reasoning techniques to evaluate the reasoning abilities of LLMs. First, we introduce textual chain of thought, TCOT, which involves LLMs gradually working through a series of intermediate steps or sub-goals using text prompts before arriving at the final answer. These steps form a thought chain that guides the model to the correct result. Next, we describe symbolic chain of thought, SCOT, which employs Python instructions to support logical reasoning. This method consists of three main steps: analyzing the information to decide the next action, generating instructions with Python commands, and simulating outcomes by executing these instructions and reviewing the results. We also present Program of Thoughts, POT, a new approach for numerical reasoning that separates computation from reasoning. POT breaks down the problem into programming commands and uses a language interpreter, like Python, to run the code. This method enhances reasoning by executing the generated code in a programming environment. For supervised fine-tuning, we define the training objective for table QA instruction fine-tuning on table instruct, which involves evaluating table-related questions and answers from a dataset. In terms of implementation, we carefully design consistent prompt templates for different reasoning methods to ensure fair evaluations. We also set formatting rules for LLM outputs to avoid irrelevant information affecting the results. For open-source models, we work within a transformer environment using multiple A100 GPUs, while for proprietary models, we use official APIs. We fine-tune various open-source LLMs on the table instruct training set, using a cosine annealing scheduler with a specific learning rate and training over 3 epochs, employing the Atom optimizer. Finally, we evaluate 34 models with sizes from 7 billion to 110 billion parameters, including both open-source and proprietary models. We assess various open-source LLMs like Llama 2, Llama 3, and Code Llama, as well as proprietary models such as GPT 3.5 and GPT 4. Additionally, we fine-tune TABLELM based on several models to further investigate the table QA capabilities of LLMs. Section Summary. In this section, we introduce various reasoning methods for evaluating the capabilities of large language models, LLMs, including textual chain of thought, TCOT, symbolic chain of thought, SCOT, and program of thought, POT, each employing different strategies for deriving answers through incremental reasoning, Python commands, and code execution, respectively. We also detail our implementation approach, including uniform prompt templates, supervised fine-tuning, and the evaluation of 34 LLMs across different architectures and sizes. Section: Automatic Evaluation Metrics. In this section, we discuss our approach to evaluating the quality of generated answers using the Rouge-L metric, which measures how much the generated responses overlap with reference answers. For the POT method, we require a specific format for the code outputs and use the Rouge-L metric to evaluate the final answers, ensuring consistency with other reasoning methods. In chart generation tasks, we analyze and execute code from LLM responses and create strict test cases to check the accuracy of the generated charts, focusing on the precision of the y-axis fields, using the pass-at-1 metric for evaluation. Our main results, presented in a table, show that over 30 advanced LLMs were tested on the TableBench. GPT-4 stands out, outperforming other models in many tasks, especially in complex reasoning scenarios, including numerical computations and analytical tasks. A model fine-tuned on open-source data with TableInstruct performs similarly to GPT 3.5, confirming the effectiveness of our training data. However, humans still outperform all LLMs in these tasks, although some advanced LLMs, particularly those using proprietary methods, show promise. In our category analysis, we find that most models excel in fact-based reasoning tasks, but struggle with numerical reasoning due to the complexity of mathematical calculations, especially those requiring multiple steps. Data analysis tasks demand more sophisticated analytical skills, such as using correlation coefficients and linear regression, which challenge the reasoning abilities of LLMs. Chart generation is particularly difficult, requiring strong coding skills and strict adherence to instructions. Smaller models show significant weaknesses in this area, indicating their limitations in handling complex tasks. Our reasoning methods analysis reveals that methods incorporating reasoning steps perform better on TableBench than those that draw conclusions directly. The TCOT method shows consistent and superior performance across various tasks. The POT method performs well in numerical computations and chart generation but struggles with textual reasoning. We identify that the performance of the POT method is limited by the success rate of code execution, as we only generate and execute code once without correction strategies. Even the best-performing model, GPT-4 Turbo, has a code execution success rate of only 78.67%, highlighting the need for LLMs with strong code generation and instruction following abilities, while also showing the potential of the POT method. The Scott method adapts well to tasks requiring both numerical and textual reasoning but falls short due to its reliance on simulated outcomes rather than actual code execution, increasing the error margin. Regarding the consistency of our evaluation methods, we note that despite the constraints on output format and standardized annotations, the Rouge-L metric may not fully reflect real performance due to the flexibility of LLM outputs. We compare evaluations from GPT-4 and human judgment to assess potential biases, using the Pearson correlation coefficient to analyze consistency across different methods. Our results indicate a high level of agreement, confirming that our constraints are effective and that our metric accurately represents LLM performance on TableBench. In our analysis of instruction following, we observe that small LLMs show different performance trends compared to larger models. The non-reasoning method, DP, performs better for small LLMs than reasoning-based methods. Most models demonstrate good instruction following with the DP method due to simpler instructions. However, small LLMs struggle with the POT method due to inadequate code generation capabilities, leading to lower executable code rates. The iterative reasoning steps required by the Scott method also present challenges for smaller models. Our comparison of the DP, Scott, and TCOT methods shows that at low parsing ratios, overall scores improve as parsing ratios decrease, indicating that some models, like Struct LLM, have strong table understanding but weaker instruction following abilities. The right side of our analysis shows that while the DP method excels in instruction following, it has a performance ceiling, whereas reasoning-based methods have significant room for improvement. The POT method's curve suggests that increasing the parsing rate could greatly enhance overall scores. Section Summary. In this section, we evaluate the quality of generated answers using the Rouge-L metric and analyze the performance of various advanced LLMs on tasks like chart generation and numerical reasoning, finding that while GPT-4 excels, human performance remains superior. We also identify that reasoning methods, particularly those incorporating multiple steps, generally outperform direct conclusion methods, and we highlight the challenges faced by smaller models in executing complex tasks due to limited coding capabilities. Section: Data Efficiency of TableInstruct. In this section, we examine the data efficiency of TableInstruct during the supervised fine-tuning process. We create datasets of different sizes by sampling from TableInstruct at rates between 20% and 60%. Our findings, illustrated in a figure, show that even with just 60% of the samples, the model maintains over 90% of the performance seen with the full dataset. The complete dataset offers the best knowledge coverage, allowing the model to perform at a level similar to GPT 3.5, while the inference costs are significantly lower, highlighting the efficiency of TableInstruct. In related work, we note that table question answering, QA, has expanded greatly, thanks to the creation of strong datasets that help advanced algorithms understand semantics better. Key datasets like WTQ, SQA, and TabFact have established benchmarks based on question-answer pairs from HTML tables on Wikipedia. However, these datasets often depend on specific table cell content for answers, which doesn't fully capture the complex queries we encounter in real life. To address this, new datasets like Toto, OTTQA, and Fedica have emerged, encouraging models to provide answers that extend beyond the explicit content of tables, thus improving performance for real-world questions. Additionally, Finca and 8QA focus on numeric queries, primarily using financial tables, which require models to interpret, compute, and extract detailed information accurately. Other datasets, such as Wiki SQL, Spider, and Bird, introduce logical expressions to train table QA models, enhancing their reasoning abilities through logic-based problem solving. Despite the progress made by large language models in table QA, there remains a pressing need for benchmarks that truly reflect the reasoning complexities found in real-world tabular data. TableBench stands out as a comprehensive benchmark that incorporates these real-world challenges into its evaluation, effectively addressing the shortcomings of existing benchmarks.